Okay, hello everyone and welcome back. We will continue our introduction to surface theory. So before we have defined the, so our setting, and recall, is that we have an immersion of a surface into R3. And from this, we obtain two symmetric bilinear forms. On the tangent bundle. T sigma, and we call these forms. So first one is given by taking the inner product of derivatives of this immersion, and this inner product is with respect to the ambient Euclidean metric. So this is the ambient Euclidean inner product. We also obtain a normal map. We should think of this normal map as a mapping from the surface into the two sphere, and this is given by n is equal to, so one particular choice of a normal, at least locally, is this. Now, of course, it is not always possible for a general immersed surface to choose a consistent normal across the whole surface. So there are examples of, for instance, immersed Mobius bands and immersed Klein bottles, which do not admit a consistent global choice of a non-vanishing normal. But locally, at least you can always make sense of this. And if your surface is in fact embedded, then it is possible to choose a globally defined normal map. So you should think of this as the unit normal. And this induces an orientation on the surface. When we define the other symmetric form by, so we defined it this way. And in local coordinates, this looks like has components hij, which is going to be the inner product of di dj psi with n. This is the same thing as minus dj psi di n. So in some ways, you should really view the this is minus the derivative of the normal map in local coordinates. Okay, and then subsequently we were able to write down some principal curvatures. Kappa 1 and kappa 2. These are these are the eigenvalues of this 2 by 2 matrix. And then we were able to write down the Gauss curvature. Which you should think of as the determinant of Hij. And then because it's the determinant of the product of these two matrices, it ends up being the determinant of Hij divided by the determinant of Gij. Because once again, when you have the indices raised here on G, this corresponds to taking the inverse matrix. And so the determinant of G upper Ij or G upper Jk is going to be 1 over the determinant of G lower Jk. All right. So this actually gives you a very nice interpretation. So there's a geometric interpretation of this Gauss curvature, which you obtain from this formulation of the Gauss curvature. And of course, you can write this as the product of the eigenvalues. So the Gauss curvature, write it this way. Okay, let's unpack what this is saying. So first of all, I have a mapping now from my given surface I started with into the 2-sphere. And this image will be some domain in the 2-sphere. And when I compute its area, I get exactly the total integral of the Gauss curvature. And there's something I need to be a little bit careful about. Which is that this area is counted with multiplicity. So what do I mean by that? I mean that the normal map may cover certain portions of the 2-sphere multiple times. And whenever I cover those portions of the 2-sphere multiple times, I will count that area multiple times. The other thing I have to take into account is the fact that if so many times this the Gauss image, the Gauss map, this normal map will be orientation reversing, and in that case the area will count negative. So this area is counted with multiplicity and according to to orientation. Right. So, for instance, if we have a minimal surface, the Gauss curvature will be negative. We'll see that in a second. If we have minimal surface, the Gauss curvature will be negative, and thus the this integral will be negative. So the area will actually be counted negative, and that comes from the fact that when you have a minimal surface, this mapping from the starting surface to the two sphere is actually orientation reversing. Okay, so this gives us a nice interpretation of the of Gauss curvature. So let's recall we had the Gauss curvature. So we had the kappa 1 and kappa 2 are the eigenvalues of H, I, J, G, J. We defined the Gauss curvature was the determinant of Hij, which we could write as this ratio of determinants of the second fundamental form divided by the determinant of the first fundamental form. And we recognize this as, because the determinant of this 2 by 2 matrix and kappa 1, kappa 2 are the eigenvalues, is the product of the principal curvatures. H, I'm going to define to be a half the trace of, which is a half the trace of Hij, which is a half. The trace is, of course, going to be the sum of the eigenvalues. We see here also that the norm squared of the second fundamental form, this is the Hilbert-Schmidt norm, which is, you should think of as the sum over I and j equals 1 to 2 Hij squared. So this is, of course, going to be, this is independent. This is independent of your choice of basis. Once you diagonalize, you get that this is kappa 1 squared plus kappa 2 squared. On the other hand, if I look at for H squared minus 2k, I'm going to get kappa 1 plus kappa 2 squared minus 2 kappa 1 kappa 2, which if I expand this out, I get kappa 1 squared plus 2 kappa 1 kappa 2 plus kappa 2 squared minus 2 kappa 1 kappa 2. I see that these terms here, of course, cancel. I'm left with kappa 1 squared plus kappa 2 squared, which is the norm of the second fundamental form squared. So this is kind of a convenient thing to remember, that the norm squared of the second fundamental form is 4h squared minus 2k. There is another little, there are a couple more geometric interpretations I want to mention. So the first one is, what do these principal curvatures measure? So the principal curvatures measure the maximum and minimum curvatures, planar, let me write this as planar curvatures of normal slices. Of this surface. Let me write it this way. Okay, so how do I make sense of this? Here's my surface. Let's draw my surface this way. And I slice my surface with some plane perpendicular to the surface. And when I slice with this plane, I will obtain so here's my perpendicular plane. This curve here in green this green curve here is given by intersecting with my surface. I will, of course, also have a normal this curve will also have a tangent. I see that the normal and the tangent are always at right angles within this plane. So the rate of change of the tangent vector is exactly the same thing as the rate of change of the normal vector. They both bend at the same rate as I go along this green curve, let's say parameterized by arc length. And I see that this curve has associated to it a plane curvature. Which is the rate of change of, so I should think of this as really, let me write this way. So if I have a tangent vector gamma dot, I differentiate that tangent vector with respect to arc length, and I take the length of that. This will have, this will be my curvature up to a sign, of course. And as I have, of course, a whole S1's worth of directions in which I can take these normal slices. And now I can minimize and maximize the curvature with respect to this angle theta. So I can say that kappa 1 is the minimum of kappa of theta, where I minimize over theta in S1. And kappa 2 is going to be the maximum. And the fact that these are the same things as the eigenvalues comes from really two observations. So the first observation is that the curvature of these plane curves really measures the rate of change of the normal to the surface as you follow along these normal slices, as you follow along these slices. As you follow along these sliced curves. So this kappa of theta is really the second fundamental form applied to a unit vector in a certain direction as a bilinear form. And then the other observation is just that the eigenvalues are going to be correspondingly the minimum of that bilinear form over this over all these directions and the maximum. And that's really sort of the minimax characterization of eigenvalues. So the thing to remember here is recall that kappa 1 is going to be the minimum over all theta of the second fundamental form applied to some, let's call it eta theta, where here eta theta is tangent to the surface and normal to the curve given by slicing sigma of at angle theta, and then kappa 2 is going to be the maximum of this bilinear form. So in higher dimensions, you make sense of all of this. Let's just remark. In higher dimensions, of course, I'm going to have some immersed submanifold in Rn+1. I can still make sense of the first fundamental form, the metric. I can still choose a local, so locally I can still choose a unit normal because at any point for any P in my image, the tangent space will decompose into an orthogonal sum of an n-dimensional tangent space together with one orthogonal direction. So then I can still write down my second fundamental form, can still have this nice formula as before, and this will still be minus y del bar x n. So I can still interpret the second fundamental form as minus the derivative of the normal map of this Gauss map. I still have now a map n, which I can think of at least locally, into an n sphere. And this integral of the Gauss curvature let me write it this way. This integral of the determinant of Hij is still going to be the area of the image of this normal map. Again, I have the same remarks about this area being counted with multiplicity and taking orientation into account. I can still take eigenvalues. This time, instead of 2 eigenvalues, I'm going to have n eigenvalues. And I can still interpret these eigenvalues as the principal curvatures of, so for instance, this is going to be the least possible curvature of a curve I obtained by slicing my surface with an orthogonal 2-plane, and this is going to be the largest such curvature. So these are all obtained. As curvatures of plane curves given by slicing with normal 2 planes. Right. And then I can still write down my mean curvature is the trace, which will end up being the sum 1 over and the sum of these principal curvatures. The only difference is if I want to write down my, the only difference is that in higher dimensions, if I want to write down the variational of the principal curvatures, I have to write down K, let's write it down as K L is going to be the, so I have to take the infimum over all L dimensional subspaces of TP sigma, and then take the supremum, so L dimensional subspaces, let's call these subspaces something, maybe P. This is really just the minimax characterization of eigenvalues. So there's a little bit more to say about the geometry of the principal curvatures and principal directions. So associated, so let's return to 2 dimensions. Although, again, a lot of this will generalize to higher dimensions. What do I want to say? I want to say associated to each eigenvalue kappa I is an eigendirection. Let's call them maybe theta 1 and theta 2. Now, what do I know? I know that my matrix is symmetric. So these directions are actually orthogonal. So you can think of this as saying that we can simultaneously diagonalize both the metric and the second fundamental form. Okay. So, right. So what does this mean? This means that I have not only associated, so at each point, I have the following information. I have principal curvatures. Kappa 1 and kappa 2. And I also have principal directions. Let's call them theta 1 and theta 2. And these are orthogonal. Now there's one caveat here to point out, which is that all of this breaks down. We cannot choose principal directions. In one case, in the case that the two principal curvatures are equal, these points are called umbilic points. But otherwise, if you have non-umbilic points, if you have a non-umbilic point, you can simultaneously diagonalize both of these fundamental forms, both of these 2x2 symmetric matrices, and one direction will give you the curvature direction kappa 1, the other direction will give you the curvature direction kappa 2. These two directions will always be orthogonal. So this is something important. This actually gives you a lot of geometric information about the surface. So later on, for instance, we'll see that these umbilic points. So we'll see that if you have say a constant mean curvature surface, which is not a flat plane or a round sphere, the umbilic points must be isolated. And so this will give you everywhere except for some isolated points, a nice choice of direction fields on the surface. So. And then the fact that this is a direction field with isolated singularities. So this is with singularities exactly at the umbilic points. The fact that this is a line field with isolated singularities, then this gives you a way to count an index of each singular point, and then you can actually get a lot of geometric information about these surfaces. Okay, there's one last thing I want to close with, which is an interpretation of the mean curvature, and this is going to come from our graphical formulation. So mean curvature is the first variation of area. And for this approach, I'm going to actually make this as simple as possible, and let's look at graphs. So here I'm going to have my surface is the graph of a function. And what do I know? I know that the area, so this is mapping some domain in the plane to right. So I can write down the area of my psi of omega. And I see this is all something you can work, you've probably worked out in a multivariable calculus class. And it's going to be 1 plus gradient of f squared. So what happens if I vary? So let's draw kind of this is going to be possibly a little bit misleading, but here is something like my graph of the function f. Let's draw something where I perturb this, this graph by some small other function. So this is going to be the graph of f plus epsilon w, where w is perhaps something that vanishes on the boundary of my domain. But vanishing on the boundary of domain is a small technical point, because otherwise I would have to, I'm going to integrate by parts at some point, and otherwise I would have to worry about boundary terms if I did not place this boundary condition. It's actually just a small technicality. It's not terribly important. Right. And now I can compute my area functional of this perturbed graph. So I can get my new area is going to be the integral of the square root 1 plus gradient f plus epsilon gradient w squared du. And now I can, of course, take the derivative of this area functional and evaluate it at epsilon equals 0. Okay, everything here is occurring over, so let's make this, let's make sure that we have a compact planar domain to begin with, so we don't run into problems exchanging derivatives and integrals. Otherwise, I could just restrict to compactly supported variations. So then if I have, say, a nice compact domain, or I have a compactly supported W, then I can move this derivative here inside the integral. And then when I do that, I'm going to obtain something that looks like the inner product of gradient f with gradient w divided by the square root of 1 plus length of the gradient of f squared. And then what am I going to do? I'm going to use the divergence theorem. To move the derivatives from, I'm going to move all of the derivatives onto f and write this as minus the integral of w divergence of gradient f over square root 1 plus gradient f squared. And we'll recognize this part as well, it's really twice the mean curvature of my surface, which is the graph. So what have I seen here? I've seen that really I should regard minus twice the mean curvature is the derivative of the area functional. The more formal way to say this is that the minus twice the mean curvature is the first variation of the area functional. So this gives rise to the definition of a minimal surface. This is sort of an unfortunate notation. A minimal surface is a critical point of the area functional, i.e. a minimal surface satisfies h equals 0. A minimizing surface is a local minimum of the area functional. So a minimizing surface is something that actually minimizes area. A minimal surface is usually not going to minimize area. A minimal surface is only a critical point of the area functional. So this is a little bit of an unfortunate choice of words, but this is historically how they were called. So we continue to call them minimal surfaces. And if you do a little bit more work associated to what we just saw, we say, we'll see that a constant mean curvature A constant mean curvature surface will be a critical point for the functional, which is area minus this h naught times volume. So you have to do a little bit of interpretation to understand what is the enclosed volume supposed to mean. But anyways, this gives you a nice physical interpretation. So the physical interpretation is that a minimal surface corresponds to a soap film, whereas a constant mean curvature surface corresponds to a soap bubble. Okay, we will stop there for now, and we will continue the next time.